T. Number 4 should have been identity. Number 8. Weren't you guys just setting entries equal to each other and solving? I'm pretty sure. So then x should end up being -4, and y should end up being 9. X was -4, y was 9. Number 32 was one of those operation-y ones where it was kind of easy as long as you didn't mess up some of the numbers, sadly. It was kind of easy as long as you didn't mess up some of the numbers. Some of you might not have fully realized what you were supposed to do, but guys, haven't we learned find x? Right? X marks the spot. We wanted x, so then you could have just added the 4a divided by 3. There were a few different ways of doing it, but ultimately, long story short, you had to take the A matrix, multiply it by 4, take the B matrix, multiply it by 2. Either multiply each of them by a third or multiply the end result by a third, which is what they did, and the final result is way down here. -8 thirds, 2 thirds, 8 thirds, 0, 4 thirds, -6. They took the 1/3 in. Maybe some of you guys left the 1/3 out, but they took the 1/3 in. Number 44, though. What did you have to do? Over. Good. Going across with going down is what you would have had to do if you had to do it by hand. But thanks, Lainey. What were you allowed to do in number 44? Nice. Go, team. Get in, and we got it okay? We know how to multiply using our calculator. That'll be very helpful on the calculator portion of the test. Okay. Number 62. Okay. This one you could have gotten a little bit mixed up on. But here's the crazy thing. The notation was a little weird. The notation is a little weird. There is that formula that we talked about just briefly. You might have needed to go to the section to talk about it a little bit more. How you can rewrite a whole system of equations as the coefficients times the variables equal the constants. But guys, where did you end up, or where were you supposed to end up? Oh, isn't that just section 8.1? So it was meant to be a review problem. All that was weird was how they wrote it, and that they showed you, hey, now that you know multiplication, you can actually write it a little bit better. There can be an in-between step between the system of equations and what you guys would get in order to do RREF, reduced row echelon form by hand. You know, the problem we worked on all day, basically on last Tuesday, I think, last Monday or Tuesday. Because you learned multiplication, they just showed there technically is supposed to be an in-between step where you take all the coefficients away from all the variables. Here's all the coefficients. Here's all the variables. You're taking all the downs and taking out the acrosses. You're kind of like, you take all the coefficients and then the variables. So there's just an in-between step. That's all that's new in section 8.2. There's an in-between step, and then you rewrite it, and then RREF to the very, very end. And the very, very end, you ended up, or you were supposed to end up being 2 and 3/2, 3/2. It was all RREF. 2 and 3/2, 3/2. Or that could have been 2 and 1.5, 1.5 technically, right? If you got the decimals. Oh, that was the last even, huh? All right, I had the section open though. Kiddos, where'd we get stuck? $69. Okay, anything else besides 69? I'm going to 69 while you guys are looking. I'll ask again. Don't worry, I'll ask again. But for right now, number 69. Okay. Number 69 gave you, oh, those numbers aren't too bad. I mean, they're kind of nasty, but they're all nice and even. Electronics manufacturer produces 3 models of LCD TVs, shipped to 2 warehouses. Oh, 3 types of TVs, 2 warehouses. Okay. Yeah, it's a 3x2, exactly. So if you figured out the 3 types and the 2 warehouses, you could have kind of figured out the meaning. Sorry. There we go. Anyway, the prices per unit are represented by the matrix. $699.95, $899.95, $1,099.95. Compute BA and interpret the result. Here's the nice thing, kiddos. You could have definitely used your calculator on this one because of the nasty numbers. I wouldn't have had you doing that by hand. Why did it have to be B times A and not the other way around? Good. This is a 1/3, and this is a 3/2. Right? So we needed the 3's to match. So when you multiply b times a, if I was to write the b right here, there we go. I know it took a while, huh? Now I have the $6.99 and the $8.99 and the $1,099. Do you guys see how the first price would get multiplied by the first number, right? When you do cross down. So this must be how expensive these TVs are, right? This must be how expensive the version A or model A is. This must be how expensive B is, and this must be how expensive. Exactly. And as you go to the next column, yep, A is still that price, B is still that price, C is still that price. So you're multiplying models with the appropriate prices. And they're in two different warehouses, which is why you have two different categories of numbers. And so when you do multiply all together, you would get a 2 by 2. No, you get a 1 by 2. I apologize. Because that's a 1 by 3. That's a 3 by 2. That matches. For my kiddos that went ahead and solved it out, I think the numbers are actually kind of big. What did you get for the first number? 1,000? 17. Ooh, more, huh? Okay, just read off to me. 1, 7. 1,729,950. Oh, bummer, because it can only hold in so many numbers in its matrix. By hand, kind of, because of the price. Okay, so in order to get it precisely, AJ is just warning us that in the actual matrix menu, it rounds this. It doesn't let you put in the full decimals because it doesn't expect you to put in a matrix with that many numbers. So then she went ahead and had to kind of do this guy by hand, but we just talked about how you could do it by hand. You could multiply in your calculator, like you could write it out. This guy times that guy in the home screen, plus this guy times that guy, plus this guy times that guy. That would have gotten you that first number. Oh, you got a different number? Oh. Because the 3 got multiplied by the 3 different models, but they all got added together for the first warehouse. And then the 3 got multiplied together for the 3 different models, but got all added together for the second warehouse. So when you were supposed to interpret what was going on, interpreting the result, here's the result, but what's the interpretation? You could look at it this way. The 3's match, so you get a 1 by 2 as a result. But then you can also think about kind of the way I just did. Well, isn't this just kind of showing the inventory for each warehouse? So it's how much all the inventory is worth, how much the inventory is worth at warehouse 1 and at warehouse 2. Does that kind of make sense, guys? So it's how much the inventory is. So for instance, if warehouse 1 burned down last night, what would they go claiming for the insurance company? I know, but this is what they'd be claiming as far as the merchandise that was lost. Does that make sense? Anyway. Thanks, Nick. Okay, we're saying it was an accident. All right, my crazies, here we go. Section 8.3. The question, do you guys see how if there was a corporation or a company or whatnot, I mean, this might be a bit of a stretch, but do you see how organizing information in matrices might be helpful as far as being able to quickly do calculations like, oh, hey, we have all these different products here, all their different prices, here are the 10 different warehouses. Like, I don't know. It's a nice way of organizing. That's the whole point of a matrix, is that you can organize information. And not only can you organize, you can also do operations very quickly in the sense of, hey, I need to multiply all of our products by all of their prices and figure out all the inventories in all our different warehouses. Oh, sweet. Throw them in matrices. Anyway. Here we go. 3. Inverse. AJ was helping us a little bit at the very beginning of class if you were listening to what she was talking about. She was talking about, I think Algebra 2 kids are just now learning trig. In geometry, you see SOHCAHTOA, I'm pretty sure. You definitely see Pythagorean theorem, right? In geometry with a squared plus b squared is c squared. Okay. You might see SOHCAHTOA a little bit in geometry, but you really dealt with trig as far as the trig functions, as far as Choshikow didn't even come up until Algebra 2, I think, with cosecants and secants. So someone was asking AJ for cosecant, like, hey, can't I just use the cool sine negative 1 button? And what would her answer and my answer and hopefully your answer be? No, because sine negative, the button in your calculator does not mean reciprocal. What does it mean? Inverse. So sine to the negative 1 means sine inverse. And what does inverse mean? Well, it undoes, but it means undoing, right? It's the undoing of. I know. I pointed to it. Okay, an inverse undoes a quantity, so it means let's undo. Kiddos, why? Why did I give this example underneath inverse undoing quantities? How do you solve for x? Undo the addition by subtraction, right? Inverse operations, you've been learning them actually since middle school. You just didn't maybe fully realize it. What's the inverse operation of addition? Subtraction. Now, hopefully we can mental math some of this because we're cool like that, right? Go carefully, and I will try as well. Wait, why is another inverse operation necessary? Undo the multiplication with, what's the inverse of good? Division. So divide both sides by 2 and you get, okay, 2 inverse operations were necessary. Okay, why did I put this example for inverse now that you're in pre-cal? You have to undo the e, but can you undo yet? What do you undo first? Good. Undo the division, you get e to the 2x is equal to 4, yeah? Ooh. Can you guys do mental math with ln? No. It's not as bad as you think. Can we do that? Mental math. Ln of e, ln of 4. We're okay? Now I can write it. Right? ln of both sides. Now, I would have to undo again with division, right? So I'd have ln of 4 over 2. Or if you want to be super cool, let's see if you can follow this math. X is equal to ln of 2. Some of you would do that illegally. Why? I know, that's the illegal one. Because you can't just divide the inside. It's 1/2 ln of 4. And what can I do with numbers written in front of logarithms? Make them a power. And what's 4 to the 1/2, aka square root of 4? 2. So if I had ln of 9 over 2, if I had ln of 9 over 2, would it be ln of 9/2? No. ln of 9 over 2, 1/2 would be ln of 3. Okay. Anyway, the point is not to review ln's necessarily, even though I got to kind of sneak it in. The point is we're about to undo matrices. Now, we're not going to necessarily totally understand how to undo matrices. And P.S., you might want to get your calculator out and have it ready. Because the calculator can undo as well, which is super nice and super helpful. Because if I was to ever ask you for an inverse of a 3x3 or a 4x4 or a 5x5 or anything above a 2x2, I would have you using your calculator. You would not be doing it by hand. We're only going to learn how to do by hand the inverse of a 2x2. And then we're going to learn how your calculator will help us for anything higher that we need, okay? So first of all, we know that an inverse undoes, so check it. We know that this is notation for an inverse, yeah? So here's matrix A. We've been talking about matrices, fine. A matrix A. A matrix A times his inverse will be the identity. That's how a matrix gets undone. It goes back to its original. Think up here. When you subtracted by 7, the additive identity was left, 0. When you divided by 2, the multiplicative identity was left, 1, right? So here, when you're multiplying a matrix by his inverse, the multiplicative identity, the identity matrix will be left. You guys already wrote that down. Let's keep going to this example. This example does not say solve. Praise the Lord, because you don't know how to yet. It just says show. Well, how do we show that they're inverses of each other? Well, what should happen if I multiply A times B? Yeah, you should get the identity matrix. And what size identity matrix? Technically a little baby 2 by 2. If you needed to write that, it's a little baby 2 by 2. We could check it real quick and see if we were to multiply A times B, does it actually end up equaling the identity? It should. It should. So, cross down. What do you guys see? -1, right? Plus 2. So -1 plus 2. I have to cross down again. First row, second column. What do you see? +2 minus 2, right? +2 plus a -2. If you're keeping track, so far we have a 1 and a 0. Ooh, it's looking nice. Now it's time to go second row, first column. -1 plus 1. 2 minus 1, or 2 plus a -1. Extra nice. Got it. Now, I'm not going to do the work. Guys, if it is truly an inverse, what should happen if we go the other way according to that little yellow box you wrote down? It should also get us the exact same thing. And guess what? If we were to rearrange and multiply, we would also get, at the end of the day, and that's how we could say, hey, guess what? Because I get the identity whichever way I multiply, B must be A inverse. B must be A inverse. Because whichever way you multiply it, you get the identity. So, here's the dealio. If they were to ask us to find the inverse, could we just go ahead and randomly start multiplying by all these random 2 by 2s until we get the one that makes 1, 0, 0, 1? We could, but that would be awful. Does anybody see any patterns between this matrix and what we found out to be his inverse? The same thing, kind of. Michael, what do you see? Okay, so he's actually looking at the multiplication and seeing why the 1, 0, 0, 1 come about. And you're totally right, that is why. They're going to end up canceling each other out for here because the signs will be opposite, and for here because the signs will be opposite. But can anybody see any patterns about how to maybe make the inverse? Let me give you a clue. This one's a little tricky because there's so many ones. It's kind of hard to see. Can I show you another inverse matrix? I'm about to show you this one. I'm going to say find the pattern. And hold on, only for 2 by 2s. This pattern only works for 2 by 2s. That's why we're going to use the calculator for anything higher. Okay. If I were to give you A, hold on. Okay, that's a random A. I just made it up, but for a very particular reason, I made it this way. But that's okay. This is a matrix A, totally random. Okay? Ready? It is inverse. There's one of those, but not 2 of those, right? I saw this. What was Chris showing when he did this? Good. So, flip the, can I call it the main diagonal? Is that okay? Flip the main diagonal, the main left to right. That's the same one as the main or the leading diagonal for the identity matrix. So we flipped those 2, right? But what else happened? change the signs of the opposite diagonal. Now pause and go look at the example we just did. Does the same pattern work? Did we flip? Joe, come on, bud. Did we flip the main and change the signs of the opposite? But it was harder to see because of all the repeated numbers. There were all those ones everywhere, so it was harder to see. But did we flip the main? Oh yeah, that went there and that went there. And did we change the signs of the opposite? Now let me show you one that's just a little bit trickier, okay? So far, this is what the pattern seems to be. So far, this is what the pattern seems to be. And this is totally right. One more. What if I was to give you this one? Bless you, bless you. Okay, I want you guys to go in your calculator. Let me show you how to use the inverse button. Let me show you how to use the inverse button. And then let me show you how the pattern really is similar, even though it's going to look like it's nothing alike. It's going to look like it's not even similar at all to the examples we've been doing. Still a 2x2 though, so the pattern should work. I want you guys to go ahead and make a matrix B for me, a 2x2. I guess you could call it A if you really want to, but that's kind of lame. Get in your calculators. Go to the matrix menu. Just call them B. That way we're all on the same page. Make a 2x2. 3, 2, negative 5. 3, 2, 4, negative 5. Second matrix. Matrix B. I want you guys to look where we normally do matrixy things, isn't it, in the matrix math? See if you can find me anything to do with an inverse in that menu, okay? I'm putting in my 3, 2, 4, negative 5, 4, negative 5. You guys are looking in that second matrix math menu because that's where REF was, that's where our REF is. Maybe you're thinking that's where we're going to find it. You're looking. Anything with a -1 or an INV for inverse? No. Ugh. Yeah, hey, actually that has to do with row operations, how we can change rows. There's also row addition and row subtraction, R1 plus R2. Anyway, you can actually check the row operation step by step. It just takes a lot of time, which is why we just go very carefully. Get out of there. The inverse is not in there. Go get matrix B. Some bad math is about to occur because the programmers made it that way. Some bad math is about to occur because the programmers made it that way. What have I told you guys this button is for right here? No. What have I told you this button is for? Reciprocal. Reciprocal. This button's the reciprocal. For instance, what's the reciprocal of 0.25? It's 1/4, right? What's the reciprocal? Reciprocal is just 4, right? What's the reciprocal of 2? 1/2, right? This is a reciprocal button. Now, sine inverse, cosine inverse, tangent inverse, these are all actual inverses, but this is a reciprocal button for any number. But guess what a programmer thought? He's like, well, you know how -1 can be used for many different things? He thought, okay, even though it's going to have a different meaning, the -1 is in there, so why don't I just make it mean inverse for matrices alone? Try it, B inverse. Try it, B inverse. Ooh, is it nasty? It is nasty. Wait, this can't be right. Something's wrong. This button must not work. Wait. What do we do with nasty decimals? Math. Math frac. Make it a fraction. Whoa! How did... Now, hold on. I've seen it for like 2 seconds. I'm actually horrible at memorizing numbers. But can you guys look and see if I get the same thing as what's on your calculator. Okay? It's going to be negative 5 over and 3 over.
Oh, wait, no. She's talking about the inverse.
And negative 2 over and negative 4 over. Now, I haven't done the overs, but are my numerators right? My numbers are different than yours?
Yeah. Yeah, the negative 3 is the only negative.
Oh. Pause. I'm not as wrong as you think. What have I done so far?
I don't know.
I've flipped the main, and I've opposite the opposite. Now you're looking at it, and you're like, no, the signs are all wrong. But pause. 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 What if I divide by negative 23? Now am I right? So what was different was not the flipping of the main or changing the opposite. What was different was a negative 23. Where did that come from? Can anybody figure out where the negative 23 came from? Can anybody play with the numbers in the matrix? It came out of here. Where did the negative 23 come from?
Oh, wait.
Multiplication of the main.
Oh, and then adding the multiplication of it's the matrix.
Negative 15 minus 8 is negative 23. So pause. Maybe the pattern is a little bit harder than we thought. Maybe we need to flip the main, change the signs of the opposite, and then number 3, divide by, if I was to call this, let's see, A, B, C, D, couldn't I make it A times D minus B times C? Or if you want to think about it, main minus the opposite. I wonder if that's a thing. Struggle. There are so many different ways of doing it. There we go. Let's do this one next. Is there an actual formula for it? And the answer is yes. Determinant of a 2 by 2, given an A, B, C, and D, there is this thing called a determinant. We'll talk way more about them in section 8.4. But there is this term called a determinant. And a determinant says, hey, you can multiply A times D, the main, minus B times C, the opposite, the main minus the opposite is actually called something special. It's called the determinant. The determinant is to matrices what dot products are to vectors. It's something special that gets used kind of in lots of different applications. But there is a special formula for finding the inverse of a 2 by 2. And if you guys notice, dividing by is like multiplying by 1 over. They switched or flipped the main, and they changed the sign of the opposite. Now there is this little term down below that you guys are going to write called invertible, and we're going to define that term on the next page, invertible. AKA, this is only going to work if AD minus BC is not 0, because we can't divide by 0. That won't work. But the nice thing is if you need to divide by 0, if this guy, the determinant, is 0, it's an impossible problem anyway. It's an impossible problem anyway. Because there's this little term called invertible. That little invertible means an inverse exists. Some matrices just don't have inverses, which is kind of weird for us because every operation has an inverse. Addition can be taken away with subtraction. Multiplication can be undone with division. E to the power of can be undone by ln. It's kind of weird to us that something wouldn't have a way of being undone, but maybe in life, bless you, that makes a little sense that there are some things that just can't be undone. But coming back, if a matrix can be undone, we call it invertible. AKA, its inverse exists, which we kind of are used to the word invertible a little bit from back when we covered inverses. There is this new term, though. Non-singular is another way of saying that a matrix exists. Invertible or non-singular. Singular, well, sadly, that's a matrix with no possible inverse. And what we just saw, no possible inverse, that's always going to happen whenever the main minus the opposite equals 0. Whenever the determinant equals 0, it's going to be an impossible inverse to find. Here's one other quick note at the very, very bottom. No unsquare. Non-square matrices will never have an inverse. Non-square matrices are always singular. Non-square matrices will never have an inverse. The only ones that can possibly be undone are the square ones. The 2x2s, the 3x3s, the 4x4s, and beyond. The 1x1s, the 2x2s, the 3x3s are the only ones that can even possibly have inverses. So kiddos, we saw a formula for finding the inverse of a 2x2. To be honest, it's the easiest, it's the best way of finding the inverse of a square matrix. We might go ahead and peek at, there are technically two different alternate methods. There are technically two different alternate methods that you could use, but the formula is the nicest, the easiest. And what did I just say as far as when would be allowed to use your calculator? Anything above a 2x2, you'd be allowed to use that cool little -1 button. So as we finish off today, can we use the formula to find two more inverses? What's the very first thing we'd have to do? Okay, we could do that. Flip the main. What do we do to this guy? Change the sign, but hold on. Wait. We learned there was actually one extra piece. I have to do 1 over, what's A times D? 6 minus B times C? 2. What would my final be? 1/4 times this guy, which I fully trust that we could multiply if we needed to, right guys? Okay. What would happen though if we ever had to divide by 0? No. It's an error. The inverse does not exist. Bye, cool kids. I'll see you later. 8.2. Sorry, 8.3. Due tomorrow. 8.3. Due tomorrow. Bye, guys.